Okay, so let's start. So before we start with what we're going to talk about today, I wanna respond to a couple of good questions that I got in the office hours. Basically, clarification, some of the clarifications that might be required for what we talked about last time, where we talked about gradient descent. So one thing that I want to clarify, I mean, this is really the space we're playing in, right? So we have some high-dimensional space. In this case, it's, I don't know, 2.5 dimensions. We have points, purple and red points. There is a linear separator, the blue line there, that is defined by W and theta. That's what we are after. So you can think about it. If you have problems thinking about this in the high-dimensional space, take your middle school, high school case where you plotted this straight line as y equal ax plus b. You can write this with W and theta. The W is going to be a comma 1. The theta is going to be minus b. And basically, that's what you're after. And you want to think about it this way. So the blue line is the set of all points that satisfy yx satisfy y equal ax plus b, or in our case here, the set of all points x such that wx equal theta. All the points above it are the set of all points wx greater than theta. All the points below it are all the points that satisfy wx less than theta. And we are looking for this w and theta. Now, we don't directly look at w and theta, but rather we define a notion of an error. You can define error many, many different ways, and we talked about it at length last time, and we're going to talk about it more. We define an error using the notion of a loss for a given point. This is the Q here. And then average of the loss over all our data set is what we call a risk or an error, which is the E in this case. And that's the function we're playing with. So we're going to change W by observing what happens to E, the error, not directly. And what does that mean? So here I'm defining algorithmically what we're doing. We define E as this average over the M data point that we have of the loss. And then we want to minimize it, and we found that we minimize it by changing W. At time t, our W is this. At time t plus 1, it's going to be this one, where we basically subtract the gradient of the error. So the picture that I want you to keep in mind is this. The error is a function of W. Some W's, like this guy here, it looks like a point, but really this W is a vector. For this W, this is the value of the error. For this W, this is the value of the error. Every W that you give me gives rise to a specific value of error, and we're trying to find those W's for which the error is small. And the goal of the algorithm is basically search W's, and we're not just doing random search, we're doing search by stepping down this error curve using the gradient to find good W's, those that have a small value of error. So that's the algorithm, and in fact, that's a relatively generic algorithm, the type of algorithm we're going to see many, many times this semester. Questions on this? Yeah.
When you were doing it yesterday, or sorry, on Monday, you were speaking of it as if the error was a continuous function, and you were differentiating it and using information from that to determine how far down you're going.
Right.
But when I'm thinking about it in terms of points, it's not going to be a continuous function, right? You're going to somehow approximate what that derivative is. Is that what we do?
No, the function is a continuous function. It's, for example, okay, let's hope it's going to go up here. Basically, the function that we worked with on Monday is a quadratic function. That's what I wanted. Okay, just a second. Let's see what's happening here. So we worked with the green function. You can think about the blue function that we're going to use a lot this semester. For every value of x, there is f of x, which is the predictor that you have. In our case, it's this w dot product x. That's f of x. And the function is a continuous function of this, right? So the square loss is basically this. Now, f of x is a real valued number. Y, in our case, could be plus minus 1, but still, the function is a continuous function. So again, make sure that we introduce a lot of notations very quickly. Make sure that you can map this to something that you can feel and understand this. So what is f of x? What is y? Why these are interesting functions, and so on. Hopefully you will you'll get this. So in the recitation, the last 2 days, actually the TAs talked about loss functions. Hopefully many of you were there. I don't know yet. Oh, in fact, one is today. Yeah. So the second one is today. So go and see. They're going to talk about loss functions, among other things, and answer any other questions you have. Other questions on this? Okay. I didn't understand the question. Okay, so let's move on. Last time we started talking about decision trees, and before that, let me just mention that. Where are we? Okay. So as far as I'm concerned, I think we have no more waiting list. All the people that wanted to be and came to class and told me that they want to be there are in the class. If that's wrong, let me know. Anyone is on the waiting list? No, okay. In fact, we have a little bit more than the allowed number of students in the class, even though there are a few holes here. I assume some people are too tired and count on the videos. But I'm assuming that some people just forgot to drop the class and they will, maybe after they see homework 1. So I will talk, homework 1 will be released on Monday. I'm going to talk about it more on Monday. Meanwhile, I assume that everyone submitted homework 0. A few of you that did not got email from me yesterday, and I think by today everything should have done it. I want to release the solution, but we had to wait until everyone submitted it, including all the people on the waiting list. I want to remind you that we give 2 recitations every week. The days and locations are on the website, and it was also announced on Piazza. There are going to be quizzes every week, just to remind you what we're doing. Hopefully this doesn't take more than a few minutes of your time. We typically release it on Thursday night, and it's always due on Sunday night. Okay, this is just a reminder. I'm going to remind you again on Monday. We only have 5 homeworks in the class, so it's, I don't know, on average 2 to 3 weeks per homework, but it's time consuming. So please don't wait until the last day and start working on it there, because you won't make it. So please start working on it when you get it, and ask questions. Okay, so let's move on. Any other questions? No questions. Okay. So we are talking about decision trees, which is a different algorithm than most of the algorithms we're going to talk about in class. We discussed what are decision trees last time. It's really a very natural representation of data. Here is the representation. Basically, that means that when you give me data that has multiple features, I can, and I'll show the data in a second. Here is the data. This data has 4 features: outlook, temperature, humidity, and wind. Each feature has a few values. Outlook, for example, could be sunny, overcast, or rainy. Temperature can be hot, medium, or cool, and so on. Given this data, I want to be able to re-represent it in a compact way as a decision tree, so that later on I can evaluate it. So in this case, I represented this data as, first look at the outlook feature. I'm just reading to you what this representation is. First look at the outlook feature. If it's sunny, go to the left. Now you're basically only thinking about those examples for which outlook is sunny. Check the humidity feature. If it's normal, say yes. If it's high, say no. That's how we read it. And given this representation, every example that you'll give me, I'll be able to classify it into yes, no. So the question for us, so the evaluation is very easy, and the question for us is how to learn. And we gave a generic algorithm last time. The algorithm is conceptually very simple. It basically says, take the set of examples. We're going to call the algorithm ID3, parameterized by set S, set of attributes or features, and the labels, which is what you see here. And basically, the algorithm goes as follows. It finds the best attribute under some definition of best, splits the data to all the values, to subsets that satisfy specific values of this attribute. So if I found an attribute that we call A here, for each possible value V of A, let's say that A is Outlook, the values are sunny, overcast, and rain. So I'm splitting the data to 3 data sets. Those examples that satisfy Outlook is sunny. Those that satisfy Outlook is overcast. Those that satisfy Outlook is rain. And then I continue the same algorithm for each S subscript V data set. That's it. And we're going to run this algorithm today. So really the key issue that we discussed at the end last time is how do we do it? How do we choose the best node? Our goal, hand-wavingly, is to find a small decision tree because we feel that the smaller the decision tree is, the better generalization it's going to give us, which is true. But finding the smallest decision tree under various definitions of smallest is actually computationally hard, NP-complete, and therefore what we're going to give is really a recursive, greedy heuristics. Think about it this way. You have a huge number of decision trees that can be consistent with the data. Or in fact, you have a huge number of decision trees. Many of them are consistent with the data. And you want to find one of them. So we're going to search this huge space, not by touching each one of them and asking, are you consistent with the data, but rather with using some heuristic that says, let's first find a good root node, eliminate all the trees from a huge search space that do not have this root node, and let's continue. Find the next node to split on, eliminate all the others, and then keep on going. That's basically what we are doing. So it's a search algorithm in this huge space without actually going back. We just make decisions. We never regret and go back to change our previous decision. It's a greedy algorithm. Okay, so at the end of last time, we started to think about how do we choose a good root node, and I wanted to give you some intuition for that. So we discussed this data set, 2 features, A and B, 50 examples that satisfy 0, 0, 50 examples that satisfy 0, 1. They're all negatives. No examples that satisfy 1, 0, and 100 examples that have 1, 1, and they're all positive. And the question was, which attribute should we choose first, A or B? And you suggested A. The vote was for A. If we split on A, we get this kind of tree. Very small tree, the smallest possible tree. If A is 1, it's a positive example. If A is 0, is a negative example. If we split on B, on the other hand, it's more complicated, right? So if you split on B, it's good. You know that it's a negative example if it's 0. But if it's 1, then you have to ask another question. You have also to check what's the value of A. And that's why you preferred A. Now, there are many ways to think about it. One, you can say it's a smaller tree. You can also think about it as how many queries would I have to ask in order to label the example, given a random example. So give me an example. You know nothing about this example. Maybe it's pulled from this distribution that I show here, 50 like this, 50 like this, 100 like this. you don't know which example it's going to be, how many questions will I have to ask until I figure out what's the label of this example. So in the top one, clearly it's one question. In the bottom one, it could be one question. On a quarter of the examples, it's one question. On 3/4 of the examples, it's actually two questions. So on average, I need to ask more questions. So that's one way to also quantify the complexity of this tree. Okay, so that's where we ended up last time. And now the question is, what if I change the data set a little bit, and now I have examples that are A = 1, B = 0. They are negative examples. I have 3 like this. So that's my new data set. That's what the change that I've made. Instead of 0 examples, now I'm going to have 3 examples. What should be the first attribute we select? Why A?
I basically want to select an attribute which partitions the number of data points
Almost?
Almost equally. So the number of data points going in one branch is almost equal to the number of data points going in the other branch. So here it will be 103 and 100. They're almost equal.
Okay, so that's one suggestion. I want to split it evenly, and if I choose A, it's going to do it. Any other argument? Yeah.
You maximize the number of points that can be satisfied with one query. This way.
Okay, so that's a slightly different argument. That goes more in the direction of, after one query, what do I know? How much uncertainty about the label do I still have after the first query? And if you look at it, the trees are going to look the same now, given that I changed the data set, right? So if I split on A, and A is 0, I know the label. But if it's 1, I still don't know the label. I need to ask another question. So I get the same structure as I had for B before. Once I put the numbers here, though, so like this, you don't know what to say. Once I put numbers here, maybe you want to say that you choose A. We can use, again, your argument, which says, essentially it says, if you choose an example, you know nothing about this example, on average, how many queries will you have to ask? So in the case of A, in about half the cases, after one query, you know what happened, right? In the case of B, on a random example, only in a quarter of the cases, you know what's going to happen. And in 3/4, you have to ask another query. So that's something that would give advantage to A. But of course, we need to quantify things in a better way. So what we're going to do now is basically introduce some notions from information theory that will allow us to quantify this and actually develop an algorithm. So we already saw this. The notion that we're going to introduce is the notion of entropy. Entropy of a set of examples relative to a binary classification, a binary label, is defined this way. The entropy of a set S is the sum of P plus log P plus, P minus log P minus, where P plus is the proportion of positive example in S, P minus is the proportion of negative examples in S. So if all the examples belong to the same category, the entropy is 0. Think about why. So in one cases, we'll have log of 1, which is 0. And in the other case, we have log of 0 times 0, which is also 0. So the entropy is going to be 0. If the examples are equally labeled 0 plus and minus, then let's think about this as log base 2. So P plus and P minus are both a half. log base 2 of a half is -1, but I have a minus in front of each one of these. So I have minus a half, minus a half, so I get 1. Minus of what I said, minus a half, minus a half, so I get 1. So basically, the entropy here measures the level of uncertainty. It's 0 if I already know what's happening. It's 1 if I have no idea what's happening. And of course, I can generalize this to the case where I have k values, every discrete distribution. So if I have, rather than 2 options, I have k options, the distribution is going to be P1 up to Pk, and the entropy is going to be the sum Pi, log Pi, to the negative sign. So let's just think about it this way. So here are 3 distributions over 2 values, plus and minus. Which one is going to have the lowest entropy? The left one, this one. Because I basically know that the label is plus. This one is going to have the maximum because I have no idea what's happening. And this one is going to have something in the middle. Okay, so really entropy is between 0 and 1 in this case, and it measures how much do I know about the labels. And already it gives you an intuition that maybe it will be relevant to choosing the root label. Now, we can try the same thing with k values. So in this case, the distribution could look like this. I have here 8 values. Which one is going to have the lowest entropy? The one on the right, this one. This one is going to be somewhere in the middle. What's going to be the entropy of the one in the middle? 1 is one option. Another option. Eight is another option. So we are assuming here, for example, just to make things clear, that the log that we're taking is base 2. What? Okay, why 3? 3. That's the right number. Log base, basically what you have here is Pi is an 8, right? So we have a sum over 8, a sum 1 to 8 of 8s, which is going to be 1. And what is log 8? Log base 2 of 8 is -3. And I have a negative in front, so it's going to be 3. So basically convince yourself that the max value here will always be log of k. Okay? Another comment that sometimes bothers people, shouldn't bother you, is that it doesn't matter which base I'm using. It's only a constant factor. It's going to be easiest to think about log base 2 all the time. Okay, you knew that once. Now you know it again. Okay, so now that we have the notion of entropy, we can go back to the decision tree problem, and we're going to use it as a way to choose the best attribute. So I'm going to define here the notion of an information gain of an attribute, and this is the expected reduction in the entropy that is caused by partitioning based on this attribute. So I'm starting with, I have a set A, I have an attribute, I have a set S, I have an attribute A, and I want to define how much will this attribute give me if I split based on it. I'm starting with the entropy of S, and I'm subtracting something. What am I subtracting? So when you look at the attribute A, it could take multiple values. These are the values here, V in values of S. And it defines multiple subsets of S, SV, right? So these are the outlook equals sunny set, the outlook equal overcast set, and the outlook equal rain set if I chose outlook, right? So I'm going to look at the entropy of each one of these subsets, S of V, entropy of SV, and I'm going to weigh them by the relative size of SV to S. So it's a weighted sum of the entropies of each one of these splits, the weighted sum of these over all the values that it takes, okay? So SV is just the subset of all examples for which outlook is sunny or overcast or rain. And now, if I have partitions of low entropy means I already know what's going to happen, then the gain is going to be high, and I'm going to end up choosing this attribute, okay? Because it's in the negative sign here, right? So if I have partitions that have low entropy, which means imbalance, I basically know what's going to happen, I'm going to prefer this attribute. Okay, so high entropy gives a lot of uncertainty. Low entropy means no uncertainty, so I want to split that lead to low entropy. Okay, so now that we have something, you can go back to our A and B exercise and try to compute the entropy and convince yourself that your intuition that A is better is indeed better according to this metric. But we are going to go back to our problem of learning a decision tree for will I play tennis today. Again, this is the data, 14 examples. 9 of them are positive examples, 5 of them are negative examples. Memorize the attributes that we have because we're going to carry it for the next few slides, and the attributes and the values each attribute has. And first of all, let's start by computing the entropy of the whole set, right? So of the label play. So as I said, we have P plus is 9 over 14, P minus is 5 over 14. The entropy is pretty large, 0.94. Okay, so that's where we start from. And now we're going to take each one of these 4 attributes, compute its information gain, and decide which one we're going to go with. So I'm not going to do all the computation in details. You can do this at home. I'm just going to give a sample of a few things so we make sure we understand the algorithm. So that's the gain of A. We're going to start with outlook. So what do we do with outlook? We look at sunny. If we look at sunny, so look here at this column. So outlook is sunny in example 1, 2, 8, 9, 11, that's it. So we have 5 examples. 2 of them are positive, 3 of them are negative. Overcast. I have 4 examples, 3, 7, 12, and 13. For overcast, it's actually interesting or simple because all of them are actually positive examples. So I already know, I don't need to compute too much. I know that the entropy is 0. For outlook equals sunny, we know that it should be pretty high because it's almost split. So, and indeed it's 971. The same thing for rainy. The split is 3-2. Also the same entropy, and so on. So now I can compute the expected entropy, which is basically the weighted sum of this entropy. So 5 over 14 from the 971, 414 of the 0, 514 of the 971. I got the entropy of this, and then I need to subtract it from the entropy of the whole set to get the information gain. That's it. So basically, that's the computation we're going to do for each node that we care about. Okay? We can move now to another one. Humidity. Humidity high is 3.4. Again, it's a high value. Humidity normal, it's pretty extreme. 6.1, it's going to be lower. And again, we can compute the expected entropy and the gain. And that's what we get. So you can do this for all 4 values. This is hopefully what you're going to get. So the information gain is largest for Outlook. That's why we chose to split on Outlook. Questions so far? Okay, so basically that's the tree we have now. We can place the values Outlook takes. And now we have 3 new data sets that we care about. One data set is the 5 examples for which Outlook is sunny, examples 1, 2, 8, 9, 11. The 4 examples for which it's overcast, the 5 examples for which it's rain. And now we start the same process. We have to do it 3 times. The middle one is easiest because if it's overcast, it's only positive example. We don't need to work. And we have to go with the process. What's that? You know the trick, right? So there is a switch on all your phones, and you can do the right thing with it.
I think it's a weather alert.
It's an Amber Alert.
So how come only one of the phones did it? Something is broken here. Okay? Okay, so let's focus on this side, this split, 5 examples. And again, I have to look at the 3 remaining attributes. In this case, I'm looking at humidity, temperature, and wind. And I need to compute, again, I'm not going to give all the details, just go over it and convince yourself that you know what's happening. It turns out that humidity has the highest gain. And in fact, that's very easy to see because if you look at the case of sunny and humidity, you see that the split is basically all the H's, all the highs are pluses, and the rest are all minuses. So basically, you know that the entropy is 0, and therefore this is going to be the highest information gain. Okay, so we decided to split on humidity. That's what we're going to get now, and you can continue this way. Questions? Yes?
And so maybe what we want to do before building up the whole tree is check maybe the other attributes to see if on the first branch they give us a higher gain or worrying about humidity. You know what I mean? So like the first thing you checked was Outlook.
Yes.
And then you went with it.
No, I checked all of them. Here. I checked Outlook, humidity, wind, and temperature.
Yeah, you totally did. All right, thanks.
So, good question. So I definitely checked all of them. I chose the best one and decided to split on Outlook. And then this is the tree I have. Only then I'm beginning to consider the subsets. The subset of Outlook equals sunny, the subset of Outlook equal overcast, the subset of Outlook equal rain, and I continue the process. Okay, and every time when I get to sunny, same thing. I'm going to consider for the set S subscript sunny, which is this set, 1, 2, 8, 9, 11, I'm considering all 3 attributes that are remaining, humidity, temperature, and wind. I computed the information gain to all of them, and I chose humidity. So that resulted in this one. And now I have to do the same process for overcast. Well, overcast we did because it was trivial, and for rain. There was a question.
I was going to say, if your variable is continuous, is there much of a difference?
No. So I already said something about it. We're going to say something about it later. Same thing. So all you need is a decision node. Whether the decision node is Outlook sunny, is Outlook rainy, or is the temperature greater than 35 degrees, For me, it's the same thing, because I can look at the data and decide yes, no. So we can use continuous variables. The only issue is we have to make them decision nodes. Okay, so that's going back to the algorithm. Hopefully it's straightforward. We start with checking for trivialities. We find the feature that has the most information gain, and then we keep on going recursively. Yes?
The optimal tree, would it minimize the entropy of all the nodes?
No, a good question.
Of all the nodes,
No. So the optimal tree, as I said, it's an NP-hard problem, and it's not necessarily going to minimize the criteria that we're using here.
No, I'm saying that the entropy of all the nodes, sum it up, and the minimum, whichever tree has the minimum amount of this, that will be optimal. I mean, so that is again what I'm defining is an NP-hard thing.
I don't think so, because that's actually very easy computation, right? I can easily compute the entropy.
You need to enlist all the trees for this.
Oh, okay, you mean after the recursion,
Exactly.
whether it minimizes. I doubt it, but I'm not sure. I think we put on the website a paper that shows that relative to several definitions of best, including smallest, including average number of minimal queries, and maybe a few others, the problem is NP-hard. You can check and see whether this is mentioned there or can be deduced from that. I'm not sure.
So does this have any guarantees?
No guarantees. Well, there are a few guarantees, but uninteresting guarantees. So again, there's been some literature on this. But basically, it's a very, very good heuristic. And people have modified, this is a basic heuristics, which I'll show you in a minute what the history of it is. And people have added bells and whistles, but basically it's good. In the problem set, you will try another heuristic. And, well, just a simple one, and you'll see that this one is better than it. So.
Why the name ID3?
It's an algorithm by, I'll answer it in a few seconds. Okay, so basically that's what we've done. History. Now I'll answer it. So basically this, like all the good things, this did not start in computer science. It started in psychology, where psychologists tried to basically model human concept learning, and they used decision trees in order to do it. So they figured out that it's a good representation and figured out, had some ideas on how to induce it. It really became an industry in the 70s, many, many years ago, where he introduced information gain. He called it ID3, no idea why. And as I said, it became an industry. A lot of famous statisticians dealt with this. Breman and Friedman and colleagues wrote a book that is called CART. I think it was in the 80s or 90s. CART for classification and regression trees. And they developed variations of this algorithm, but this is actually the algorithm that caught. Quinlan developed a series of improvements of this, C4.5, C5.0 now, I think. It used to be the most popular algorithm used in machine learning. No longer the most popular one, but still a very, very good one. And as I said at the beginning when I started, if you're looking for a general purpose learning algorithm, probably decision trees as a component and boosting or bagging or some kind of averaging a lot of decision trees, we're going to go into the details of that, is probably the best general purpose learning algorithm you want to use. And in your homework, you're going to do an approximation of this. You're going to learn decision trees, and you're going to use them as features at least part of the homework, use them as features for a learning algorithm. Okay, so now we know decision trees. I want to move to talk about some general ideas that apply everywhere in machine learning, and we're going to start talking about them in the context of decision trees. And the idea is that of overfitting. So here's a new example. Here is the decision tree that we just learned. What can you say about this example? Yeah?
Is it completely and exactly fit the data?
Let's try. Does it? We'll start with outlook equals sunny, which means we're going to the left. And then the left asks us humidity, normal, so we're going to the right. And it says yes. But the example says no. So it doesn't fit the tree. Now, someone told us, oh, you forgot this number, example number 15. You only learned for 14 example. Add this one to your training data. What should we do? There was, yes? Yeah, we can change the tree, right? So that's easy. We can basically, it doesn't exist in the tree. We're going to augment the tree. Now, we can always do this, right? As long as the data is consistent, that is, there's no contradictions, same examples with two different labels, which we assume doesn't exist now, we can always do this, right? We can always augment the data with new examples, but is this a good thing to do? So if you do it a lot, really you can fit anything because decision trees is a very expressive class. Maybe you fit noise, maybe you fit some coincidental regularities and not the masses of the examples that you've seen. And this is exactly what we mean when we say overfitting. So remember when we started talking about these things, the training data that we have is very, very tiny relative to the data, right? There's a lot of data out there, and we will never see an even a reasonable subset of it. We'll always see a tiny subset of this. So the question is, how do we think about this? And in the context of decision trees, you can think about it as I have a very, very expressive class. I can fit all the data. Do I want to? The question is, what do I want to do so that I get the best generalization, not necessarily the best performance on my empirical data. So we define overfitting using this figure here. So the complexity of the tree, or the size of the tree if you want, is our x-axis here. The accuracy that we get is the y-axis. And of course, it's natural to, you would agree that on the training data, as we increase the complexity of the tree, we're going to increase the accuracy on our training data, right? We're going to fit all the examples. Eventually, we're going to get perfect accuracy. The question is, what's going to happen on test data? And typically, what we're going to see is that at the beginning, it grows and pretty much matches. Maybe I should have had a little bit of a gap from the training accuracy. But at some point, it's going to drop because we just fit regularities of the training data, not necessarily regularities of the whole population. And this is when we say that we overfit. So a hypothesis H is said to overfit the training data if there is another hypothesis, H prime, such that H has smaller error than H prime on the training data, but larger error on the test data. Okay, so we really want to be able to stop when these curves split. Okay, so why do we have overfitting? And I'm going to use, I'm basically waving my hands here for the next few slides. Later in the semester, we'll be able to quantify some of these things in a little bit more rigorously, but still I want to give you already the intuition. So I'm going to use some terminology that I'm not going to define completely. So one reason could be that there's too much variance in the training data, right? So really, the training data doesn't represent a good sample of the instance space. And we basically split on some features that really no one cares about. There could be too much noise in the training data. And really, noise here we can think about in at least two ways. We can think about some feature values are incorrect. So this is an example that says that Outlook is sunny, but really, this was a measurement error. The Outlook was overcast. That's one type of error. Another type of error could be that the label was incorrect. They said that this example was a positive example. Really, it was a measurement error. It was a negative example. So there could be some noise in the training data, and if we completely follow the training data, we're going to, go down into sub-trees that really no one cares about. But in both cases, the result is that if we want to minimize the empirical error, the error on the training data, and we can, because decision trees are very expressive, it's going to impact us in a bad way when we go to the test data. So what can we do? Generally, we can agree to not learn the best decision tree that we want on the data. So even though you can fit all the data, we're going to prune the decision tree a little bit. We're not going to learn all the depth that we want. We're going to prune some of the leaves, if you want, or some of the nodes, and basically not go all the way with the depth of the tree. How do we make decisions? When do we decide to stop? There are multiple ways of doing it, and we're going to talk about it today and next time. Basically, you want always to keep some kind of a validation set that hopefully is a good representative of the data, but it's outside your training data. You don't train on it. And as you train, you measure how well am I doing on this other set. And this will give you some sanity check, and you're going to stop based on drop in performance on the validation set, for example. And again, there are several ways of doing it. We're going to discuss a few of them. So we can stop growing the decision tree, or we can grow the decision tree and then prune it back. These are basically the two conceptual ways of doing it. All the packages that you will use, and you will use a decision tree package in homework 1, for example, already have these options. And there are several ways to evaluating when do I stop or what do I prune. And these have to do with some statistical testing of how well am I doing with the additional layers of the tree or without. Cross-validation, which is a version of this. We're going to discuss this next time. And some other information theory-based criteria that basically allow us to understand whether the additional complexity we add to the tree gives us something or not. So basically, the goal is to keep the tree simple while still allowing it to perform well on the empirical data. So these are there's a trade-off between two goals. On one hand, you want to fit the data. On the other one, you don't want to fit it too well. And we have to be able to understand this trade-off. It's very related to a notion that maybe some of you have heard the name, the notion of regularization that we're going to use in other contexts later in the class. The bottom line is keep the hypothesis simple. So Okay, so as I said, I'm waving my hands here, but before I do this, I want to gauge your intuition because you already know something about linear classifiers. So here we are talking about decision trees and not learning all the way down. What would be an equivalent notion in terms of the complexity of the hypothesis when we're talking about linear classifiers? Any idea? Yeah?
Not using all of the dimensions that you have, but having a line.
Okay, that's one option, definitely. So basically, select subset of the features somehow. Don't use all the features. That could be an option. But this requires, again, an algorithmic tool that will tell me which features should I use, which shouldn't I use. And I want to go even simpler than that, or more generic than that. So here's the data set I have. I show it twice. You're not seeing double. So it's the same data set. I have positive examples that are red, negative examples that are blue. And I'm going to use a linear separator to separate them. Right? It's kind of like, here's my data. I'm going to use the decision tree to separate it. And in decision trees, we said, hand-wavingly, maybe you don't want to have the deepest decision tree. Maybe you want to cut down the bottom layers. You're not going to fit all the data, but it might generalize better. So what would be an equivalent thing, or an almost equivalent thing from the linear separators perspective? So I'm going to add something to my graphics to incentivize you. So here is one separator, H2. Here's another one, H1. Both of them separate the data. Which one is better? H2. Why H2? I think most of the voices I heard were H2. Yes?
Maybe the average distance between the points and the lines.
Okay. Suggestion, average distance between the points and the line. Yes?
Just intuitively, if those points are being generated from two distributions, H2 is just in a better place, sort of, if there's another random positive point that comes out, it's probably going to classify that.
Okay, so if we think about what other points are going to come up, in the case of H2, they are more likely, the new red points and the new blue points, to maintain the side of be on the same side of the linear separate as they are now, while in the case of H1, it's more likely that some red points will move to the other side and some blue points will move to the other side. Right, that was the argument here. Agreement, disagreement, other ways to say it? So one other way to say it is the thickness of the line. So while this one has thickness 0, we can think about linear separators as thick lines. So in this case, I'm able to fit a pretty thick line. In this case, I cannot. It's a thinner line. So the thickest line I can fit, the intuition is it's going to generalize better. Okay, so rather than talking about big trees and small trees, which is clearly something that has to do with the size of the hypothesis class, right? There's a lot more big trees than small trees. So if I'm choosing to use small trees, basically I'm limiting the hypothesis space, right? I'm saying, don't search the space of all trees, search only the space of all trees up to depth 8. Similarly here, I'm saying don't search all linear separators, search all linear separators with some depth, with some thickness. There's a lot less thick linear separators than thin linear separators, right? So basically, I'm also controlling the size of the hypothesis space by saying, I'm going to try to separate the data that you gave me, but I'm going to try to do it with a thick linear separator. And that's going to be some way to control my generalization, giving the argument that you just gave. If you separate the data with a thick linear separator, the chance that new elements in the data set, new red points, will jump to the other side is smaller. Okay, so that's the intuition. And that's a good intuition that we're going to carry with us when we make this actually more rigorous. This is actually going to be the new and improved algorithm to what we've done last time for learning linear separators. If you want support vector machines, it's doing just that, trying to find thick linear separator rather than just linear separators. Okay, so what are we doing here? I'm adding some notations that you'll see later on, but we want to start getting used to it. So everything that we are doing in learning is under what is called the IID assumption. By IID, we mean independent and identically distributed. Independent means every data point that we see is independent of the others. Okay, so basically, we sample data points for our training, we sample data points for our evaluation, they are independently generated. Of course, this is wrong. In most real-life situations, elements in data sets are not independent, but in order to actually study this mathematically and give some guarantees on what we are doing, we have to make these assumptions. And they are identically distributed, and by that I mean that there is some distribution that governs the generation of the data. When we see training data, it came from this distribution. We don't know what it is, but we know that there is some distribution. When we see test data, it comes from the same distribution. That's a key assumption that we're going to make throughout this class. There are some deviation from it in today's theory of machine learning, not a lot. This is still a very important assumption for us to be able to analyze what we are doing. And also to think about it. So the way you should think about it is the reason machine learning works is because we believe that what we've seen in the training is basically what we're going to see in the test. You know, if all you've seen in the training data is you know, gray elephants, and then you see a white elephant, you don't know it's an elephant, right? So we cannot do anything if the test data is very, very different than what we've seen. Okay, so under this, we can also think about overfitting. So this is overfitting, or these are the graphs of accuracy as a function of the size of the tree on the training data, growing up all the time, and on the test data, growing, and at some point, it goes down. So if we wanted to think about it from the decision tree perspective, or any other model for that sake, so it overfits the data when its accuracy on the training data goes up, but its accuracy on the unseen data begins to go down. And you want to be able to explain to yourself the shape of these curves, right? How it behaves on training, how it behaves on test. Now, we have a few notions that we need to discuss. One of them is the empirical error, which is the error that we incur on the given data set. This is a curve that you can think about. Good curve, bad curve. Make sense? Is this the curve you would have plotted for the empirical error as a function of the model complexity? Why?
Because the complexity means you think you're likely to overfit and not be able to generalize. So error will start.
But the empirical error is typically on the training data. So no. So this, I put this curve here for you to be awake and make sure that I'm wrong here, right? So this does not make sense as a curve for the training data, because as a function of the complexity of the model or the decision tree complexity, on the training data, the error is always going to go down to 0. We can always fit the data. Yes?
What if there are like data points which contradict each other, have the same data points? Then wouldn't it just like not converge to 0 then?
Yeah, it will not converge to 0, but let's assume for now that we have a consistent data set, right? So we can actually fit the data. We're going to generalize this at some point, but given that we are assuming that our data is pretty good, even if we assume this is going to be small, so we can assume that the empirical error is going to go down as the complexity of the model goes up, right? So this is the wrong curve. So really what I have here on the y-axis is some measure of the model complexity. In the case of decision trees, it could be the number of nodes, for example. Then the second term that we have is the expected error. What's going to happen in the future? And here, as a function of model complexity, it does make sense to assume that at some point, as a function of model complexity, it's going to go up because we overfit the data. That's what we said before. And now there are really two notions that we want to be able to talk about, and I see that I will not talk about them today. So there are notions of variance and bias of the models that together will allow us to quantify how will the model basically behave. So I'm going to define this early next time. Just to give you a hint, the performance, the expected error, if you want, the stuff we care about, is going to be a combination of the bias and the variance, where the bias is how well can we fit the data in the training, and the variance is basically, as a function of model complexity, how varied the model will behave as we add, for example, one data point. It has to be clear that if we have a very, very large class of models, a lot of options, then you add one data point, you're going to choose another model because it fits it better. You add another data point, again, you're going to jump to another model. So the variance is going to be very large, and that's not necessarily a good thing. Right? If you have one model to choose from, adding one more data point won't change anything. That's your choice, that's it. So if you think about these two extreme cases, you'll get some intuition for these notions of bias and variance and how the performance of a learning algorithm is a function of these two. Okay, we're going to start this from this next time. Questions? Yeah.
For a continuous variable in a decision tree, so you have two decisions which are not positively discrete things. One is how many branches do you want to make, and the second is at what point do you want to
Yeah. So it's a very good question. We'll get to it next time. So if I have a continuous variable, a continuous feature for a decision tree, I have to decide, let's say it's a height. I have to decide, how do I split the height to decision nodes? Do I split it ahead of time and say, you know, very high, very tall, medium, short? Or do I look at the values that I get, and as a function of that, I'm going to split it somehow? And that's going to be part of the decision. This is really pre-processing in some sense. Yes? Just 1 second. There's another question here. Yes? Well, I can, so as I said, think about this as pre-processing. I know that one of my features is going to be continuous, and I bucket it ahead of time into, let's say, 3 regions, and I say, if it's above 6.6, it's very tall. If it's, between 5.6 and 6.6, it's medium, otherwise it's short. So I can do this, or I can look at my data, and based on the data I have, maybe I have nothing that is above 5.6, so I don't care about the tall bucket. So we're going to discuss this a little bit next time. But basically, the idea is I can take a continuous feature and discretize it, and then everything goes the same, because I have a decision node. So we're going to give an example of this next time. Any other question? Okay, see you on Monday.
I'm just auditing without registering for the class, but I was wondering if you could add me on Canvas so I can have access to the lecture video.
Everything is going to be available on the website.
I couldn't access the lecture recordings.
Okay, you will be able to.
All right, cool.
So we'll make it available. I thought we already had, but
no,
we'll check. Okay, thanks. Yeah.
Pick the first feature as the thing that has because if we're calculating the features entropy, like every iterator, every type of that feature entropy, and that entropy is higher, and then we subtract that entropy from those entropy, then that so the feature with the most entropy in itself means that it has more variation. And shouldn't that be the so in that case information gain would be
So the way I talked about it here. Yeah. So basically, what I want is I want to be able to, as soon as possible, know what's going to happen, right? So if I want to know what's going to happen, it means that I want the least uncertainty, right?
that has more features on more data points in one feature.
Yeah, if it's completely imbalanced, I know what's going to happen, right? So I want to be as close to that as possible.
Okay.
That's the intuition, because this way, I basically no need to ask. On average, I would not need to ask additional questions, right?
I understand.
Okay.
I have a question for why is the risk expectation times by the loss, not the loss?
Not time, it's off. It's expectation of the loss.
Oh, okay, that's why there's a cluster.
Yeah, but we typically don't do that.
Okay,
Yeah.
okay.
So this is the pointwise loss for the example x, y, and we really want to take expectation over all the data.
Okay, thank you. Yeah, another is I didn't follow here, so why this makes sense?
So we're going to go back to it. It doesn't make sense. I left it here because it doesn't make sense, and I wanted to people it's the wrong graph. Yeah. I wanted people to tell me it's the wrong graph.
So I was being issued a permit to this class, and the sys department person who contacted me said that because I'm affiliated with the college, not the C's, so they couldn't register me directly through the sys system.
Yes.
So I will have to go to talk with the college office and to sort it out. So it may just take a while for me to officially get into the class.
Shouldn't take a while. I mean, just you got it yesterday.
2 days ago, actually.
2 days ago.
Yeah.
So did you talk to them already?
I wrote an email, but I haven't done a response.
Go to the office. Don't wait.
Yeah, I was just going in person.
Did you do homework 0?
I did.
Okay.
And also quiz one.
So we're not waiting on you, but
Okay,
But basically, I suggest that you just go and talk to them. It's
Yeah,
possible
definitely.
that they give you a form that I have to sign,
Okay, cool.
but it's doable. I mean, we've done this before.
Cool.
Okay.
It's just that like, because I'm waiting to get in like, officially, so I don't have access to Canvas yet. So
You
I
don't
may
need Canvas.
I
So
need-
everything we're doing is going to be publicly available.
So the PDF of the quizzes will also be.
The PDF will be made
Great.
available. Yeah.
Thank
The
you.
only thing that I hear is not available now is the videos.
I'll
but-
always be at the lecture though, so.
Yeah, but even that will become available. It's just we guess we didn't get to it. Yeah. I guess on definitely sometime. So. Yes.
I have a question. I'm George. Came to you a few weeks ago about an idea for a master's thesis. So I was just wondering if now was a better time to come to you and sort of talk about it.
So the best thing would be come to my office hours.
Okay. Yeah.
So it's when is it? It's
I think Monday, Tuesday.
Monday, Tuesday, 5 to 6.
Okay, great. Yeah.
This would be the best.
Okay. Is the the wait list stuff, has that calmed down a little bit? 'Cause-
It's done basically. So
Okay,
from
great.
my perspective, we are set.
Okay, that's great. Yeah.
Yeah. So,
Okay.
so definitely come. Next month.
Okay,
or
yeah.
Tuesday.
Okay, great. Awesome. Thanks. Bye.
Professor, I actually didn't register for this course. I mean, I was in the waiting list, but I already had 3 courses. I talked with my department coordinator. I'm from NEEM. So what they said was you can't drop a course right after September 10. So if you want to take, you can take 4 courses this semester. So I felt that taking 4 courses will be a little hectic for me. So yeah, that's why. So I'm just attending all the classes. And
You can sit in the class. There's no
yeah,
problem.
I can access all the files publicly. But the doubt is whether can I do the final project and then
No.
I mean, can I do it and then just show you? Not a formal. I mean,
We just don't have time. I mean, we have 150 students.
okay.
We cannot do homework and projects for other people. We just don't have time to read it. And
Okay, fine.
so, but next time you can register for the class.
Oh, for the next semester.
Yeah.
But
yeah.
next semester you won't be available, right? There'll be some.
Someone else is teaching. I'm teaching it in the fall. Someone else is teaching it in the spring.
So
Yeah.
what I planned was I just thought of attending SIS 519 this semester and take SIS 520.
No, you cannot do this. It's either
No, no, SIS 519 without registering and SIS 520.
you cannot. We will not allow any more people to take both classes.
No, I didn't register for this course, right? So,
Or if you didn't register, then you
yeah,
can
because
take it.
because I'm actually pretty new to coding. I didn't C, C++. I'm learning Python right now. So I thought.
So that's perfectly fine. So you can do everything that that we ask people to do in this class,
Yeah.
but we're not going to grade you.
Yeah, that's fine. That's not a problem. But
Yeah.
then can I just try the final project? I mean.
You can try it. As I said, I don't guarantee that we're going to spend time on it.
Okay, it's all right. So.
Because we, as you will see, we're going to get, 50 projects or
Okay.
something like this. It takes a lot of time.
Is it individual? I mean, is it?
It's going to be probably groups of 2.
Oh, okay, fine.
That's what we'll see. I mean, I have to figure out exactly how many students we have in 519
Okay.
before we decide.
Okay, fine. Because I thought doing the final project will be useful for me.
I think it's important, but as I said, there's so much we can do
Okay, fine.
with the TAs, and we have a very, very large class. It's already very time consuming.
Okay, fine. So your suggestion is to take SIS 520 next semester. If I attend all SIS 519, it's advisable to take SIS 520, right? The next semester, because
I think so. If you already sit in this class, take 520, it gives you a few other things, different things.
okay, fine. Okay, thank you.
Okay, sure.